question. Maybe some of her collaborators do, but many of the things that she's interested in have to do with these days is the center of our galaxy, and so we're pleased that this first talk will be on the dark mass at the center of the galaxy. And later this week we will hear other things about her research, both in a public lecture on Thursday evening and in the regular DAA time slot on Friday afternoon. So I told Andrea I and a couple of others have to leave at 3:30, and we'll stand up and say loudly, "I've had enough of the Galactic Center," and we'll stomp out. So when you see a few of us rudely leave, that's all prearranged. And with no further ado, welcome Andrea, and we look forward to your talk.
Thanks. It's a pleasure to be here.
One more seat here.
Okay. Yeah, come on up. What I'd like to tell you about this afternoon is an experiment we've been doing over the last decade with the Keck telescope to look at the center of the galaxy. And the original question was to figure out whether or not there's a supermassive black hole there. And we can test this hypothesis and understand the environment at the center of the galaxy by looking at the orbits of stars. So this is a long-term project that's been done in collaboration with a large number of people. In particular, I'd like to point out my two long-term collaborators at UCLA, Eric Becklin and Mark Morris, and then my current graduate students who have done some nice work that I'm going to present today, Tuan Do, Jessica Liu, and Silvana Yelda. All right, so as I said, there's a number of key questions that we're after, and the first is there a supermassive black hole at the center of the galaxy? And what I hope to convince you is that the answer is yes, but of course, if you want to be a real cynic, I'm going to show you how to poke at this. And once you have, you do suspect that there is a black hole, you can address the properties. And there aren't too many properties of the black hole. We can get its mass. So we can check the m-sigma relationship. Turns out, while you might, and then this is interesting because, of course, the galaxy, the black hole at the center of the galaxy is one of the smallest black holes, but it turns out sigma is the problem in our galaxy. We'd like to know what the distance to the black hole is, and because if we take that as a metric for R0, this gives us the key. This is sort of like H0 to the galactic astronomers. All problems having to do with galactic structure are scaled to R0. And in particular, one of the key questions here is people would like to know what the shape of the dark matter halo is. And getting R0 is key in understanding the shape of the dark matter halo. Speaking of halos, we want to look at a slightly smaller scale halo around the black hole. As I'll talk about quite a bit on Friday's lecture, there's ample evidence for a large population of very massive stars at the center of the galaxy. And we know through dynamical evolution that these larger mass stars in the form of stellar remnants should sink into the center of the galaxy. So the central black hole should have a little entourage or fan club of little black holes surrounding the supermassive black hole. And we can get at this directly through the orbits of these stars, because of course if there's something other than a point mass, the orbits should not close anymore. We'd also ultimately like to figure out, or these orbits offer us an opportunity to ask the question, is general relativity an accurate model in this strong gravity regime? In other words, these stars are coming sufficiently close that you're testing a different regime of gravity. We're not there yet, but I want to show you how we could get there in principle with this type of experiment. And again, if we believe that there's a black hole, we are faced with a couple of questions. One, why is it so dim? The radiative emission associated with this location in our galaxy, given that we think it's a few million solar masses, is only 10 to the minus 9th of its Eddington luminosity. So why is it dim? And there's a couple of other things that we can address in terms of its luminosity or radiation that I'll address today. We'd like to know how the black hole influences the appearance and evolution of stars surrounding it. And we'd like to know, oh shoot, somehow I lost, oh well. I lost it probably because it's actually, the last question is we'd like to know where the young stars form. Turns out that many of the test particles that we're using to, the canonical freshman physics test particle to measure the potential are young. And really, this is quite a surprise. You do not expect young stars in the vicinity of a black hole. Black holes are incredibly hostile neighbors to stellar nurseries. So this was quite a surprise. In fact, so much a surprise that I've relegated it to Friday's lecture. But I think one of the more interesting parts of the research that we're doing today. So I'm going to step back and basically tell you a story about the black hole, or the reason people got to the point where we are today. So the whole concept of supermassive black holes came from the study of AGN. We know that there's tremendous energy rate that's coming out of these objects. We know that the radiation doesn't look like anything that's emitted by stars or gas. We know that they vary on very short time scales, which suggests that what's ever giving rise to the emission is very small. And the gas is moving very fast. And so we said, aha, there must be a supermassive black hole. And of course, this is the example of Cygnus A, where we see these jets of emission, where we can figure out the amount of kinetic energy and then infer a very powerful central engine. But of course, these things are only about 10% of the galaxies in our universe. So this gives rise to the question, do normal galaxies, non-active galaxies, have quiet black holes or stealth black holes lurking at their middle? And this was a question that was raised 30 years ago by Lyndon Bell and Rees. And it's taken us a while to answer it. But if you want to answer it, the Milky Way is really one of the best places to address this question. The pro is that it's the closest center of a galaxy you're ever going to get to study. It's only 8 kiloparsecs away. The con, because of course in life you never get a pro without a con, is that there's a very obstructed view. We live in the middle of our galaxy, so there's a tremendous amount of dust in our line of sight. So in the optical, we have an extinction of 30 magnitudes. Well, that's pretty horrible. You're not going to see at the center of the galaxy at optical wavelengths. But if you go to the infrared, just 2 microns, we only have an extinction of 3 magnitudes. So we can actually see the center of the galaxy. And all the work that I'm going to talk about today has been done in the infrared, and primarily at 2 microns, in fact, in the K band. All right, because I'm going to talk about the center of the galaxy, and there's a lot of phenomenology, or it's like the zoology of the galactic center. So I thought I'd give a little overview to what's going on there on different scales, and starting maybe on a scale that those who do extragalactic astronomy can relate to, which has nothing to do with this experiment. All right. So this is a nice overview picture from Reinhard Genzel's '94 review article. On the 100 parsec scale, you see the plane of the galaxy. And what's useful to note at this scale is that in the radio, you see these non-thermal filaments. And the interpretation of these filaments is that at the center of the galaxy, there's very, very strong magnetic fields, perhaps as strong as a milligauss. Although I'll have to say this is a highly debated number within this field. So there is this question of the origin of the magnetic fields at the galactic center. The other structures that are useful for both today's talk and on Friday are these giant molecular clouds. So these are potential sites for star formation, although they're quite far out. Okay, so these are fairly massive. They're maybe 10 to the 5th, 10 to the 6th solar masses. But the densities, well, they're reasonably high for what we like to think of regular star formation, maybe 10 to the 4th particles per cubic centimeter. But in terms of what you need to get star formation to happen near a black hole, this is nothing. All right, moving on closer, there's a green blob here, which we're going to use to transition to the next scale. And this is on the 10 parsec scale. So that's the same green blob here. This is known as the circumnuclear disk. It's a ring of gas, and we can measure the motion of the gas in here, and that's going to come up in a minute. There are other structures in here that are seen in the gas. This is known as the mini spiral, and again, the gas in this structure has been useful for testing the mass distribution. And there's a nice population of stars. 90% of the stars in this region are old, but there is an interesting 10% that's very young, that's located really only in this very central region within the central parsec. Coming in close, there's this purple X. The purple X is known as Sagittarius A star. It's a radio source. It's fairly unusual. In fact, its emission looks somewhat like a low luminosity AGN. So in fact, it's been long thought that perhaps Sagittarius A star is the radiative counterpart to the black hole. So in fact, when we ask the question, is there a black hole, we're also asking the question, can we associate it with this unusual radio source? So what makes it unusual? It's non-thermal, it's very compact, and it has low velocities. Okay, so there's beautiful VLBI work that's done that, for which you, in fact, all you see in the motion of Sag star with respect to quasars is the motion of the sun around the center of the galaxy. All right, now, so people were concerned about the idea that there was a black hole at the center of the galaxy, both because there wasn't much emission, so Sag star was it, and it's a pretty wimpy source. In fact, a stellar, basically a typical star, can give you the amount of emission that comes from Sag stars. So to associate that with accretion onto a black hole suggests that the accretion rate has to be pretty low. The other problem that presented a case against a black hole in the as late as the early 90s was the existence of very young stars in the central parsec. So it's a healthy population. In this color figure, the blue stars are the young stars. These are Wolf-Rayet stars that are primarily identified here. And people argued, well, look, if you have a black hole, which is right here, the tidal forces should be huge. In fact, so much, much larger than the gas densities needed to overcome the tidal forces. And this is not a little problem. This is like many orders of magnitude. In fact, the closest young stars that have been identified, the gas densities that are needed are 10 to the 10 times higher than what's been observed. Okay, so this gave rise at that time to a very strong argument that there's no way there could be a supermassive black hole at the center of the galaxy. But of course, why take that as a reason not to check? And of course, the best way to check is through dynamics, so the orbits of stars. So if you want to prove that there's a black hole, what you need to show is that there's a large concentration of mass inside a small volume. And for a non-rotating black hole, setting all the basically taking all the gravitational constant, the speed of light, and setting this to number, you basically get that the mass of the black hole in units of mass of the sun times 3 gives you your Schwarzschild radius. Okay, so a simple way of calculating what size is the relevant size to squeeze some mass into. And we're going to use stars as test particles. In fact, the first, you can use anything as a test particle. You can use gas or stars. And we're going to start off with the gas. But as you'll see, gas can be pushed around by a lot of other things. So there's 2 methods. There's the patient and the impatient method, or sometimes I like to call this the pre-tenure and the post-tenure methods. So the impatient method is where I started, which is when I first showed up at UCLA, and that's you measure velocity dispersions, and you make a lot of assumptions about projection effects. And in fact, as you'll see, we got ourselves in all sorts of trouble. So this is a way bigger problem than I had ever anticipated, and this experiment, I think, is a useful warning to all those who love to use projected mass estimators. So this business is you measure the projected velocity dispersion either along your line of sight or in the plane of the sky, and you've got a 2-dimensional radius, and then you have to make assumptions about your projection of velocities and positions. Okay, but it gives you a useful estimate. But you're doing this in an ensemble way. And basically, you're doing statistical averages and making assumptions about your stellar population. If you're patient, you can actually get the 3-dimensional orbit. So you can take one of these stars and have it go all the way around. And in fact, when we started this experiment, it was quite clear that if it was in fact the case that all the mass that had been inferred was in the form of the black hole, this patient method wasn't crazy. Okay, it wasn't insane. And the power of this patient method is that you get rid of all your assumptions, and you confine the mass to a much smaller volume. So you're much more confident that it is a black hole. So let's see how this argument was built up. The initial hint that there was a black hole came from radial velocity measurements. So velocity dispersions made from spectra. So you're looking at the velocities along the line of sight. You're looking at line widths primarily. And it was primarily measurements in the gas. So the earliest measurements came from neutral hydrogen in the plane of the galaxy. That's the blue stuff. The green, which is conveniently color-coded to the green blob, was that the green ring, the circumnuclear disk. Well, these 2 measurements gave no hint that there was dark matter. This dotted line is what you infer from the stars. In other words, if you just count up all the stars, either by number counting the stars or looking at the light distribution. And it turns out that we're going to have to be careful about that ultimately. But in this case, either game gave you the same answer. So you add up the light, you use some assumption about the mass to light ratio, and get an enclosed mass estimate. So this is enclosed mass as a function of radius. So we're out at 100 parsec. That was the cartoon, the original cartoon. Here we're down at 3 parsecs. So this is the scale of the second cartoon. But life got interesting when people started making measurements in that mini spiral coming in from the ring. And this is work done by Charlie Towns. And there, at 10 microns, they could detect the neon lines. And there, the velocity dispersion gave were too high, given the projected radius. So that was the first hint that perhaps there was a black hole, or at least a concentration of dark matter on order of 3 million solar masses. Now, at this point, this is sort of the late 80s. The criticism of this work is that gas responds to a lot of forces. There's strong magnetic fields in this region. There's lots of high-mass stars, which have lots of wind. So there's lots of reasons that gas can be pushed around and to give rise to higher velocities than just the gravitational influence of a central dark mass. So that gave rise to a second set of experiments that were started in the early 90s. Looking at stars. Stars respond principally by gravity. So you're much more confident that when you measure a velocity dispersion that you're actually probing the gravitational potential. So on top of the gas measurements, I've overlaid the stars, which are the yellow and orange. And that confirmed this suggestion that there is a very strong concentration of dark matter within 0.1 parsecs. Now you might ask, well, why wasn't this at this point enough to argue that there was a black hole? And in fact, if you read these papers, they're very indirect about even suggesting the possibility of a black hole. And the reason is that you're pretty far out. You're many thousands of times the short shield radius out when you're out at 0.1 parsecs for a 3 million solar mass black hole. And there were a lot of alternatives. So at the time, the argument was primarily the lifetimes of clusters. So you take a cluster of any type of object that you want, anything that's dark, your favorite dark object cluster, neutron stars, little black holes, whatever. You can ask what the collisional lifetime is and the evaporation lifetime is, and it's quite long compared to the age of the galaxy, which means that it's a viable alternative. And of course, the theorists went right to work and came up with other alternatives in the form of the fermion ball hypothesis, which is the idea that these dark matter concentrations that were suggested not only in our galaxy, but for other galaxies, including the active galactic nuclei, were fermion balls. So it's sort of the equivalent of a neutron star made of neutrons, but in this case, of fermions. You pick the fermion, this will give you a mass. Okay, so if you want to rule out these alternatives, what do you need to do? You need to cram that mass into a much smaller volume, which means that you need high spatial resolution. Of course, this is where I got excited, because this is what I had invested a tremendous amount of time in doing, in figuring out how to compensate for the Earth's atmosphere. So this gave rise to 2 independent experiments. First, the initial one was started in 1992 by Reinhard Genzel on the NTT, and this was continued until 2001, and then transferred over to the VLT in 2002, and then my group, which started in 1995 at the Keck telescope. And it's been tremendously helpful to have these 2 groups sort of going at it for the last 10 years. We keep each other very, very honest, and it's a hard experiment. I mean, I cannot understate the difficulty in making these measurements. The measurements have been made with 2 different techniques over this time scale, and there's been huge technological improvements which have really changed the kinds of measurements and the kind of experiment that we can do over the last 10 years. So this has been exciting work to do. This little animation shows you the center of the galaxy. It's just some of the first images we took. This is a 5 arc seconds by 5 arc seconds on the side. It shows you the problem of the atmosphere. Atmosphere is continually distorting our images. Basically, you lose a factor of 20 in angular resolution because the atmosphere changes on very, very short time scales. So speckle imaging, which I call poor man's AO, is basically you take a bunch of short exposures, short enough to freeze the effects of the atmosphere. You bring it back home, and you realize that every single star in your field of view has been affected by the atmosphere in the same way. In other words, your point spread function is the same, something that we're used to in lots of contexts, but it usually doesn't look quite so cruddy and change on such short time scales. Nonetheless, you can figure out how to make a picture that looks pretty gross, actually, over here. And it has a Streller ratio of about 5%. 5%. That's really embarrassing. But there's 5% of that's diffraction limited. And in fact, that's the same. So it's 5% of the energies in the diffraction limited core. People got a lot of experience with this kind of image when Hubble Space Telescope was first launched. That's exactly the situation that we were in. And what we learned from that experiment is that you can do astrometry. You can measure the positions of stars very well. You just need a diffraction-limited core. OK, you've got a huge halo that affects your ability to go deep over in crowded areas, but you can get very precise astrometry. We'd love to do a lot better, which is what we do with adaptive optics. So instead of having to take short exposures, what you see here is that you have the light from a science target and the light from a reference star, or ideally laser, which is where we are today. And they're affected by the atmosphere in the same way. Of course, this is the exact corrugation is changing on this 1/10 of a second time scale. You have a deformable mirror. So if you think of this as the atmosphere, so above the atmosphere, these are flat pancakes. Go through the atmosphere, you've got a Pringle. So this is like one funhouse mirror. The deformable mirror basically undoes what the first mirror, the atmosphere has done on these very short time scales. You send the optical light or some portion of the light off to some wavefront sensor that's figuring out what the atmosphere is doing, and you get to collect and integrate for more than a 1/10 of a second, which was amazingly gratifying. And what does this do? Well, this allows you to take images that are much deeper. A 1/10 of a second isn't much integration, so you're always read noise limited. You just can't get very deep. So we can go much deeper. We can take images at multiple wavelengths. This Speckle game really only worked at 2 microns. Now we can get some sense of what the stars are doing. And most importantly, we can take a spectrum, which gives you a lot more astrophysics, not only in terms of being able to measure the line of sight, the velocity along your line of sight, so you get 3 dimensions, but you also get to learn about the stars themselves. All right. I want to do a little ad here because I know adaptive optics has been very long in the coming, so I don't think there's yet the true believers in adaptive optics. And I have to say, I've really become a true believer. You can tell this because I stopped doing Speckle in 2005. That was the point when I actually bought into this technique. It really works. It's great. It's like a revolution in high-resolution imaging. It basically, you now have a 10th magnitude star wherever you want in the sky. Okay, this is tremendously powerful because now you can take pictures that cover big fields of view, but more relevantly for most people in this audience, you can point at any target that you want because now you've gone from sky coverage of 1%, which is a very specialized technique, to a sky coverage which is almost approaching 100%. From my point of view, laser guide star AO also had a huge, huge effect in terms of my ability to do astrometry. And so while moments ago I bragged that speckle imaging could get you good astrometry, and I used to get really excited about 1 milliarcsecond astrometry, we've had an order of magnitude improvement starting in 2005, which gets us down to 0.15 or 150 microarcsecond. So this is, again, a whole new level of astrometry precision, which means that there's a whole new class of problems that you can envision doing if, again, one only has the patience. So we basically had to restart the clock. So this speckle imaging started in 1995. This is 2005. But this experiment has been sufficiently successful, and the possibilities of what you can do with this improved astrometry is really powerful. This is just a PR thing for those of you who have trouble envisioning what a factor of 20 means. I mean, sometimes I like to say, you should envision if somebody told you they'd pay you a factor of 20 more. That's a big deal. So, the resolution improvement here is also quite powerful. So this is without adaptive optics. This is with. This square here is centered on Sagittarius A star. So really what we're trying to measure with this impatient method, what we started with, is we want to see speedy stars in here and slow-moving stars at larger radii. So in fact, it's a very simple experiment once you get beyond the technology. Okay, so the sources that dominate our current knowledge of the central dark mass were discovered with speckle imaging. So this is our yucky picture, and this is the central arcsecond. Huge gradients here. Those gradients are from the halos of bright stars nearby, but nonetheless, you see these stars, okay? And what we do is we take images. We just take images. And you look for how these stars move on the plane of the sky. And I like to show this image mostly for the graduate students. So when I first was hired in 1994, I wrote my first Keck proposal. And I said, I've got this great new idea. I know how to do speckle. We can, follow up Tom's work and see if this black hole is there. So the first thing they said is, one, your newfangled speckle technique isn't going to work on the Keck telescope. And two, even if it does, you won't see any motion. And at that point, you wish you could send the time allocation committee back to freshman physics, because that's really all you need to know to say this is going to be an easy experiment as long as speckle works or any of your techniques. So this is a picture in 1995. This is a picture 4 years later. You do not need a computer to tell you that these things are moving around. And today we track, actually this number is outdated, over 2,000 stars in a 10 by 10 arcsecond field of view. So there's a lot of stars to play this game with. All right, so again, in the early days, what we're doing is velocity dispersion. So again, it's quite simple. You measure position in the plane of the sky versus time. So again, this is like freshman physics. This is north-south position versus time, east-west position versus time. You only need 2 points to measure a velocity. You need three points to believe it. So actually, after we measured the first 3 years is when we published our first result. We get an enclosed mass here. So we get the same. Well, we get roughly the same mass, but we've confined it to a much smaller radius. So before we were at 0.1 parsecs, now we've confined the mass to 0.01. So that increases the dark matter density by 3 orders of magnitude. Okay, so what have we done for ourselves yet? Not much, except, well, actually quite a bit. I shouldn't say not much. We've ruled out the possibility of a cluster of dark objects. In other words, now the time scale for a cluster of dark objects, the lifetime is shorter than the age of the galaxy, so you argue, well, it's unlikely that you're catching such an unusual object, and it must be a black hole, but the fermion guys were kicking in at this point. And here it's actually really useful to look at what mass we were coming up with in those days. So you use the virial mass, you get 2.5 million, and this is all assuming a distance of 8 kiloparsecs, because we didn't have any way of probing it, so you just take the best known value. The Bacall-Tremaine, you get 2.7, the Leonard-Merritt, 2.6. So everyone was pretty convinced that we had it pretty much right. And then came, oops, I misspelled their name, Chakrabarty and Saha, who said, you guys should be using these non-parametric mass estimators, and you would be getting an even lower mass at 1.8 million. Okay, so that's where we were. We were pretty convinced that that was the right mass estimate. But it was worth continuing, because of course, if that's the mass, these stars should be making orbits that have pretty short orbital periods. In other words, shorter than your lifespan. So it was worth continuing. And so this is the modern version of this animation projected forward. So of course, this is really an animation here. So I'm just taking the stars that we know about and plotting our best fit orbits. So what I've done is I've used the best fit black hole properties. I've assumed that everybody is following or is influenced by the same black hole, so it's a simultaneous fit. Although what I will say, and this is I think this is a really new realization, that while for a long time we were very excited that there were a lot of stars in here, it's really only this star that matters for our determination of the black hole properties for a number of reasons that I'll get to. But this guy has an orbital period of 15 years, so we've basically been going at it for almost 15 years today. So the way this animation works is that if you have a solid trail, there are real measurements there. So for the speckle images, we got down to about 16th magnitude. This animation became more complicated once AO came online, because we discovered a lot more stars, because now we're going 3 magnitudes deeper, which is really exciting, because there are a lot more things in here. But there's a lot more things that are basically have very short trails, just to indicate we really don't quite know yet. We're in the early days, but we can make guesses. But anyway, we've got astrometric solutions. Okay, and here's where you need to go back to your classical mechanics to figure out, well, what do you get for knowing an astrometric orbit? Well, what you get, it turns out, free of assumption, is the dark matter density. And it turns out that that's tremendously useful, because this argument about what kind of object it is a density argument. So you up the density by quite a bit. And as I say, SO2 is the guy we're going to use primarily. The reason that is because for the black hole, you get a mass that's divided by R naught R naught cubed. So it's mass normalized by R naught cubed. But then your closest approach is a semi-major axis, which has R naught. And then when you use Kepler's law, it becomes cubed. So the R naughts cancel out. OK, so you know what's going on here. Hopefully this will go. OK. Shoot. OK, but today we actually also have radial velocities. So we don't have the time baseline because it basically kicked in when AO started. It actually kicked it in when we had natural guide star AO. Wasn't very good, but allowed us to get spectra of this object, which means we have radial velocities dating back from 2000. And we really didn't understand the orbit back then, which tells you why we didn't sample this like crazy, because we really should have been going berserk in this era. So this is radial velocity as a function of time in units of thousands of kilometers per second. So it's gone from basically plus 1,500 to minus 1,500 in the space of basically 3 years. But nonetheless, you can put it all together, which allows you to decouple the mass and the distance. And it also allows you to find the position of the black hole. So you can find that to about 1 milliarcsecond. And you know it is definitely smack on Sag A star, as well as you can locate it. I'm sad to say I now appreciate all these details of reference frames, which I used to think was all so boring, but now I care all too much. So anyway, we can do this. You get this. One of the important things that we've recognized was, one, that reference frame matters. And so if you start to ask us about your reference frames, you might see me squirm a little bit. But the other thing that's really important is that there are a lot of stars in that field. I mean, if you watch that animation carefully, you could easily see the paths of stars cross over. It's not that they're colliding, because of course in 3D these things are quite far apart, at least at the level that we're probing, but they're going to interfere with each other. And they interfere at a very important point. In fact, now that we've detected Sagittarius A as an infrared source, your points at closest approach are biased, and you shouldn't use them. So for anyone who's actually been keeping careful track, I suspect there's not too many, but if you really are watching this field, you'll notice that the reported distances have been floating around by quite a bit. And that's because of these systematics. You have to be careful about source confusion, which is why the brightest source that you have an orbit for, which is this guy, is your best bet. And this is also the one that's the shortest orbit. And the other thing, as I said, is you have to watch out for reference frame issues. Nonetheless, having said that, I'm quite confident that this is the right value, as best as I can get on top of all the systematics, which is basically a mass that is still correlated with R naught. Okay, so this is important to recognize. So if you have astrometry only, you get a mass that goes as R naught cubed. If you only have radial velocities, there's a degeneracy that goes as R naught. So the fraction of astrometry to radial velocity tells you wherever you are today. So there's some curve. But anyway, you need to be very careful when you compare mass estimators to what the assumed R naught is. Or not assumed, but best fit is, because there's actually a strong correlation between these two quantities. Nonetheless, it's sufficiently well determined, and you really have the closest approach pretty well nailed. In other words, you confine it to within 100 AU. Okay, so this mass, which is 4 million times the mass of the sun, was located within 100 AU. Okay, so this, compared to earlier estimates, increases the density by 10 to the 7th, and you've really increased the argument here. So this is the classic plot that's shown by Maus in 1997. This is the density. Dark matter density is a function of black hole mass. Here's all, at the time of this publication, these were all the supermassive black hole candidates. The lines here are the lifetimes of those stellar clusters. So in other words, you need to be above the green line to rule out the dark matter cluster. So the useful thing to take away from this is that most candidate supermassive black holes can have this alternative quite happily. And it's only 3, I've actually updated this plot a bit. There are only 3 galaxies in our universe for which we can confidently say or rule out the dark matter cluster. So that's M31, NGC 4258, and our galaxy, which started out here with the Charlie Towns experiment, was brought up here with the high resolution velocity dispersion, and we're now up here with the orbit. So this, in fact, is the best case, most convincing case for a supermassive black hole at the center of a galaxy. And you can now flip this around and say now you have a great laboratory for studying all sorts of phenomena associated with black holes at the center of the galaxy, because of course this is the closest galaxy we're ever going to have to study. Now, what next? Well, there's all sorts of things you can do with orbits. And as I said in the beginning, one of the things you'd like to do is start to test relativity in all its various forms. And it turns out that with the radial velocities, we're actually not that far off from testing some effects, which, I mean, right now we only need classical mechanics, right? We're not assuming anything about special or general relativity, but it would be cool to start seeing those effects. So this is the measurements that I showed you a moment ago. The radial velocity is a function of time. Our current precision in radial velocities is 25 kilometers per second. This is the predicted deviation from a Keplerian orbit as a function of time at closest approach. So you can see that there's a huge deviation from the classical orbit when you go through closest approach. And the amplitude is 200 kilometers per second. So that should be easy for us to measure. We just need a little bit of patience because we got to see it go around again. And that's going to happen in, I think, let's see. It's year 2002, 2009. So we're not that far off when we've got patience. And what you get for this is the special relativistic transverse Doppler effect and the gravitational redshift. So again, this is kind of exciting, well within our technological reach. We just need patience. Now, what else? Well, you'd like to actually see it in the other domain, and there's actually a lot of effects that you can see if you can start to see the astrometric signatures. And here's where I really want to emphasize that the astrometric measurements are really limited by those unknown sources. You kind of saw it with the confusion of the 15-year guy at closest approach. It turns out that it has a huge influence. And this is actually for that star. This is the average astrometric error as a function of distance from Sagittarius star from the underlying stellar population. So with Speckle imaging, you expected it to be about 1 milliarc second. That was our measurement error. We never noticed it. AO, it's about a half a milliarc second. Well, we're at the 0.1 milliarc second level now. We see this. It's really easy to see. In fact, for a long time, I was starting to see these stars that made S's, and I thought, oh, we're seeing binaries, until I realized the scale of the S was our resolution limit. So you're just seeing stars run over stars you don't know about. So we can discover other things, but it also means you need to do better. You need higher resolution, better AO, and I think in this crowd, you know where that goes, right? This means that you need TMT to overcome the stellar confusion, to study all your long-term goals of testing general relativity and all sorts of other things that you could do if you could achieve the true resolution, this true precision, without having to worry about confusion. So we did a bunch of work. This is work that I did with Nevin Weinberg and Milosavljevic when they were at Caltech. We put it in the science case, but they were good citizens and actually published it in AppJ's. So what do you get with TMT? Well, you get higher resolution, and we made some assumptions about how well the AO system will work there. And so you can ask, well, how many stars will you see? Well, basically, you probe deeper to fainter magnitudes because your confusion limit is decreased. So at 10 meters, we can go roughly to 18th magnitude. At 30 meters, we can go down to 24 magnitudes, which means instead of seeing about 10 stars in the central 1 arc second, we get to see 100 stars in the central arc second. And that's powerful because, one, you have more tracers, but also powerful because you actually know about those guys, and they're no longer sources of confusion. Okay, so we tested this with a simulation. And of course, with all simulations, they're highly idealized. So we assumed that the TMT TAC would let us play this game for 10 years. Seemed like a reasonable assumption, given that we've been able to do this at Keck. We made very conservative estimates of the astrometric precision, only half a milliarc seconds. And the reason that is because no one really understands how well AO, these multi-conjugate AO systems will work for astrometry. There's some big unknowns here. And so for anyone who's really interested in probing deep, I encourage you to think about this. We assume radial velocities to 10 kilometers per second, which is, again, not too challenging to get to given the increased aperture size. And what do you get for this? Well, you get to really know where the distance to the black hole is. Even if you allow for extended mass, you get, instead of 5%, you get to less than 0.1%. Why is that important? That's important because at this level, you start to probe the galactic structure. In other words, at this level of the precision, you start to ask about the shape of the dark matter halo by combining different experiments, different dynamical experiments within our galaxy. You also may be able to calibrate or test the calibration of the cosmic distance ladder. In other words, reintroduce the calibration of the RR Lyrae and the Cepheids. So this becomes an important calibration. You also get to, as I alluded to before, test general relativity. And to put this into some context, the system that people are most familiar or usually quite familiar with are these binary pulsars, which have provided a very strong test of GR. And to be honest in advertising here, there's an incredibly accurate clock here, which makes it a very powerful probe. But if you parameterize this in terms of the relativistic parameter, which just compares the Schwarzschild radius to your distance of closest approach, you're about a factor of 500 times closer with these orbits at the galactic center to the Schwarzschild radius. Okay, so in other words, you're really probing a slightly different regime of gravity than you are with these binary pulsars. So that would be interesting to test, given that this, GR is one of the least tested of our four fundamental forces. In this paper, we parameterize this as the astrometric precision one can achieve as a function of the signal to noise of the effect that you're looking for. The dotted line here is just assuming you only get to play this game with one star, the SO2. This was useful because at least we know the orbit, so we're quite confident that, if you could get the 0.1 precision that we think we can get today, the signal to noise of this effect is 10. In other words, presumably you can actually play this game with all the other stars in your field, and that's the solid line. Assuming that you can guess what their orbits will be, that's where you're going. There are other deviations from the Keplerian orbit that you might also be able to detect. The one that I'm going to get to in a minute is the extended mass distribution. Remember, we expect this little entourage of little black holes, maybe surrounding the central black hole. You'd like to test the structure of any cusp that might be forming at the center of the galaxy. So you'd like to look at the extended mass distribution. So that is the blue lines here, again, for the only one star. This star is quite eccentric. So in fact, it goes from 100 AU out to 2,000 AU. So that really allows you to probe the shape of the mass distribution between 100 AU and 2,000 AU. And again, if you use all the stars. And here, this is an incredibly conservative limit on the extended mass. All we did is assume that you only get to see what is in the light. Given that there's probably a lot of dark mass at the center of the galaxy, this effect is probably quite large. Now, if I were sitting in the audience, I might ask, but how in the world are you going to decouple these two effects? You've said, aha, we're going to see GR effects, and aha, we're going to see the extended mass distribution. And here you have to remember that one effect makes you go prograde, and the other one makes you go retrograde. So at least that, it means that you definitely need more than one star to play this game, but the signatures are very distinct, right? The extended mass distribution makes the orbits open up because you effectively see a smaller, less enclosed mass as you come closer, so you open up, and the relativistic precession is the other way. Ideally, you'd like to go and measure the spin of the black hole. I mean, black holes don't have too many properties. It would be nice to measure the spin. This is really hard. We're pushing very hard on the AO team to start to dream about this, but you can see you need an order of magnitude improvement, and you need this with a technology that's much more complicated. I think I'll leave it at that, except we'd like to do it. You'd like to measure the spin. Okay, so that's the future. So we love TMT. I'm glad I can say it in Canada that I'm talking about TMT as opposed to some more politically correct GMT or name. But anyway, let's get TMT built. What can we say about these topics today? Well, it turns out that we actually can start to address this. And one of the ways that people have tried to start to test the question of spin is by realizing that we can measure the emission, the radiative emission that I mentioned before from Sag star. And there's a long, complex history in terms of the detection of Sag star, all sorts of false starts. But now that we have sufficient resolution and an ability to take very quick measurements, that are deep, so you need adaptive optics to really convincingly do this, you can actually see that at the center of the galaxy, there is a source there that doesn't look like the others. One is variable. This is actually real data in a little movie cycle. So the white things are stars in a given night. Any fluctuations are just calibration issues. They're all fluctuating together. But here you can actually see here there's a very different source, and the color is very different. It's much redder than the starlight. So there's a number of reasons why you would say this is Sagittarius star. It's also exactly where the dynamical center is, and there's been no evidence of it moving in the infrared either. Okay, so we think that's the radiative source. And the really exciting prospect was if you look at the light curve, this is of a nearby source. This is of Sagittarius star. It's very variable on all sorts of timescales, but in these early measurements, the power spectrum suggested that there might be excess power at 20 minutes. Well, why get excited about 20 minutes? 20 minutes was exciting because if you figure out what the innermost stable orbit is for a non-spinning black hole of the mass that you've inferred, that's inside the last stable orbit, which means that you have to infer a spinning black hole if you want to say that this is emission coming from a blob located at the last stable orbit. Okay, so 20-minute periodicity suggested or gave a possible handle for the spin of the black hole. Okay, there's been lots of work in the stellar mass black hole community trying to do this, as well as the AGN community. And I think we should have taken a lesson from them, which is there's lots of reasons that things vary on lots of different timescales. And in fact, if you look at AGN in particular, they're variable on lots of timescales. In fact, they're very characteristic of red noise, which means you see stronger fluctuations on long times. I've got this backwards. On long timescales than on short timescales. And if you have a short sequence of data, you can get spikes. Okay, so that's the lesson learned here, is that now that we have lots of data, we can go back and look at what it's done. And you get this for free. Basically, every time you do the astrometric experiment, you just make sure that you don't integrate for more than a minute, which is long compared to the 0.1 seconds that we used to do. So, and you get these beautiful light curves. And you get all sorts of characteristics at 2 microns and 10 microns, and you add them all up, or at least you look at them individually. You see spikes in different places. But you add them all up, and it's a beautiful red noise power curve that has a power law that looks exactly like an AGN. So in other words, I think what we're learning about is the accretion flow. And that's complicated. It gets really messy. There's a whole community of people. I'm involved in it, but I'm not sufficiently excited to tell you about it because it's a mess. So there's all sorts of campaigns to correlate the X-ray to the infrared to the submillimeter. And it's sufficiently variable that this is a hard game to play because, yes, you can say, aha, there was a peak here, and aha, there was a peak a few minutes later, and try to correlate them. It's more likely that you're just getting tricked. So I think that the community has to make a much bigger investment than we've made today before we can say too much about the astrophysics of this accretion flow, except that it's probably driven by MHD instabilities, and we have a lot of lessons to learn from what's going on in the sun. So I think that's my current picture, or the picture of a lot of people, that what you're seeing here is a small-scale phenomena that has to do with flares in the accretion flow having to do with magnetic fields reconnecting. But, yeah. Pardon me? Oh, 1 over f to some power, yeah. So this is f to the, let's say I think the power that was best fit was 2.5. So you see in AGN a range from 1.5, I think, to about 2.5. Yeah. There's probably a lot more to be said here and a lot more work in terms of whether or not this is one number all the time and whether or not there's a high state and a low state. But it's getting into a macroscopic view of microscopic physics. So I don't know. I'm going to stop at that because I like the gravity stuff. So the other thing we'd like to get at, other than the spin of the black hole, is this extended mass distribution. And there's a lot of reasons why you might think that there is an extended mass distribution. There's predictions that there may be 10 to the 5th to 10 to the 6th solar masses in the form of stellar remnants that have migrated into the center. So in fact, they may dominate the central cusp at the center of the galaxy. Okay. So you can actually play this game with the orbit of SO2. It's closed. It works really well with the Keplerian orbit. In other words, you really have no right to be putting in a measurement of the extended mass distribution, but you can ask for a limit. In other words, what's the limit of the extended mass distribution surrounding the central black hole? You don't know the power law, so you can put that in as a variable, which is the x-axis. And this is the amount that's inside the furthest approach of SO2, which is about 2,000 AU or 0.01 parsecs. And this is, it's basically 1, 2, and 3 sigma upper limits. Okay, not very gratifying today because you're not even limiting what you think is in the form of stars. So we're not there yet, but be patient with us. But we're not that patient either. So you have to think of, well, how else could I solve the problem today? Well, you could go back to those projected mass estimators. We have measurements of velocity dispersion, so we can try this game again and try to ask, well, where did we go wrong in the past and fix it? So I'm going to present this to you as where we are today, but I really want to emphasize today, this is built on a lot of assumptions. So we have to be very careful with the conclusions. The simplest thing you can look at is just the velocity dispersion as a function of radius. If it's just a point as a point source, you get 1 over the square root of r. If there's an extended component, it's going to start to level off. And that's exactly what you start to see, that you can actually fit this as 1 over the square root of r with a constant at 75 kilometers per second. So in other words, the velocity dispersions are starting to see the influence of the extended stuff. An important thing that we've learned since that early game is there are a lot of young stars. Oh, right. You only can play this game with a relaxed population. Okay? So you've got to get rid of the populations that you think are not relaxed. We know there are a lot of young stars in there. In fact, those early estimates were dominated by the young stars, so it's amazing that we got anywhere close to the right answer. So we've eliminated all the known young stars, but in fact, our knowledge is incredibly incomplete. So keep that in mind. So then to convert that velocity dispersion into an enclosed mass estimator, you need to know the distribution of stars. In other words, you need to know where your test particles are, because that's what gives, that's what tells you how the projections are going to go. Well, this is useful also just because people want to know whether or not there's a cusp. There's a prediction that a black hole should form a stellar cusp. And this is this is the surface density of stars as a function of radius. And at large radii, this looks pretty much like an isothermal model. And then at smaller radii, it starts to deviate. In other words, you see a depletion. So the break is at about 0.2 parsecs, which is interesting because this is also where the radial velocity constant starts to kick in. So this is evidence that there is a cusp. The power law, there are all sorts of predictions about what this power law should be. The interesting thing here is that it's flatter than almost all the predictions. So again, assuming that you've got it right, and this is hard. This is really hard because if you look at different, again, you have to assume that you are looking at a well-characterized population. This game actually was done basically just with number counts of anything that was in the field, correcting for extinction, which is variable. I mean, there's a whole bunch of caveats. But anyway, assuming that this is right, the collisions can flatten this slope. So maybe this is telling us that collisions are really important. In other words, the stellar population in here is much denser than you might have otherwise inferred. And again, there's the caveats about if there's a mixed population, which I'm going to tell you on Friday there is. OK. But nonetheless, we're going to ignore that. And if you revise it, you can get your enclosed mass as a function of radius. You get a revised estimate of the extended distribution. And you can ask, well, this is the dynamical mass. This is from the black hole. This is from not the black hole. The green line is this minus the black hole. And the red line is what you think is locked up in visible light, in other words, in the stars. And there's a factor of 2 excess. So the game right now, which is extremely sensitive to your assumptions, is that there is evidence for a cusp that's dominated by stellar remnants, which is an intriguing possibility and important because there's all sorts of theory today that suggests that there should be this intense concentration of stellar remnants, so little black holes, neutron stars at the center of the galaxy, and this may be the first evidence of this. I guess my response to this is you really want the direct confirmation, and so that's what direct orbits with TMT would buy you. OK, so in conclusion, I hope I've convinced you, if nothing else, that we have very strong evidence for a supermassive black hole at the center of our galaxy, that LGS-AO has revolutionized our research and that it works, so you should not be afraid of using it. We've learned about the accretion flow. We don't get to measure the spin of the black hole from it. It looks very much like AGN. We've learned that there's a cusp, and it may be flatter than predictions due to collisions, and it might be dominated by stellar remnants. And I think there's a very exciting future in this business of measuring the orbits of stars, in particular, and looking for these deviations of orbits as a test of GR and this extended mass distribution. And to end, I'm just going to leave this animation that shows in 3D all the well-characterized orbits that we've done so far. This is also sort of food for thought for next lecture, Friday. They're color-coded. The blue ones are young stars. The yellow ones we don't know. The red ones are old stars, which should give you pause in terms of everything I said about the stellar cusp. Okay, so thanks for your attention. Enjoy your meeting.
I won't ask you a question. Normal thinking.
Okay, so you got to bug out. Any questions? Must be plenty, I'm sure. Whaley?
You said that you would need MCAO on TMT, but why do you need MCAO? You're looking at a tiny field. Wouldn't even a single adaptive optics be all you need for the 1 arc second field?
Yeah, I would love a regular AO system, but the TMT group decided they were only going to build an MCAO system. So the question is how can you use it? And it turns out, actually, that if you want to play this game really well, you have to very much control for your reference frames. So you need to, ideally, you need to get out to things that are measured in the radio to tie into that reference frame. Well, quasars, or you can do bootstrap with through the masers, so through Mark Reed's work. And that's a 30 arc second field of view. So that's over a scale. So it's the reference frame that actually drives you to want larger fields of view. Let's see. Timescales for tidal disruptions. You mean the frequency of them?
Yes.
So naively going into this, you would say 1 every 10 to the minus 4 years. But that's not accounting for a large population of stellar remnants. So that's just assuming that the population that you see from the light is the population that you see down at the center. In other words, yeah, enough said. Yeah.
Your Reed and Backer both have done parallax measurements of Sagittarius star. Are they good enough to be of any help to you?
What they get is they are useful because they constrain the motion of Sagittarius star.
But they give you an R0 too, right?
It turns out, in principle, you can, but in practice, you can't. And the reason is because the maser spots. So their problem is that masers actually aren't static. I think this is their main reason. But anyway, it turns out they can't compete. They went into this thinking that they could. And now what they're doing is trying to measure the distance to SAGB2. And I guess the other way I would view this is if they can do this, great, because then it takes R0 out of our equation of getting all the other deviations as opposed to having to solve it ourselves. So they're still trying. We're all still trying. R0's floating around by quite a bit.
Yeah. I was wondering if you could explain a little bit more. I think you said that to source confusion during close approaches, referring to these underestimates.
Well, okay, so you have to exclude the closest approach points. And you can tell that you have to exclude them because if you look at the photometry, you can actually see that the star apparently gets brighter at closest approach. So either you could claim, aha, my star is interacting with the accretion flow, or you could recognize that you do have a source that you see when there's a star not around. So that source is presumably at the dynamical center, which means you always pull your measurements towards Sagittarius star. And you might ask, well, why can't I correct for that? And the reason I can't correct for it is because it's variable. So I don't know. It just becomes too complicated. So you throw them out. And if you throw them out, you actually get a different distance. A different distance by half a kiloparsec, although including them makes the distance go up by half a kiloparsecs. So there's still a discrepancy between the two groups because they're getting a much smaller value than I am. They include the closest approaches. I throw them out, which suggests that the real discrepancy is even larger. So then you have to start worrying about reference frames. And yeah, and it turns out that's a messy problem. It's,
What would TMT observations do for the other supermassive black hole observations? Would it bring a lot of them in?
well, ideally, what you'd be able to do is start to play this kind of game in other galaxies. So the first thing you would look at is M31 to ask whether or not you could actually measure the orbits, or at least the velocity dispersion, do the stellar velocity dispersion experiment in M31. That would be phenomenal. And in the other galaxy, again, your resolution corresponds to the scale that you confine the mass to. So you're going to confine the masses to a much smaller volume and hopefully bring a much larger fraction of those black hole candidates onto the other side of the line.
How many do you think you'll get up there?
Well, there it's only a factor of, well, it depends on which telescope you've used, but it's a factor of 10 because most of this work has been done with the Hubble Space Telescope. The other arena that I think will be very profitable with TMT is the globular cluster experiments. So again, resolution matters, and so the lower your mass, the more sensitive your measurements have to be, or the closer you need to go.
So for this diffuse light, are these actually all stars near the black hole, or are you also looking at the background from the other side of the galaxy? Do you know?
Here?
Yeah, I mean, for your contamination here.
Oh, it's tiny. And it turns out most of it's so there's two stars in my field of view that I know for sure are foreground. And I can tell because they don't, now that I have more information, they don't have the color. The colors are much too blue to be at the galactic center. So there's a small contamination from the background. But there's another neat experiment that you could do with it here. You could start to look for the lensing. And while the probability, so that we played that game back in the Speckle days, but it turned out, well, there was a bunch of candidates, but we just didn't have the information or the photometric precision to play that game. But today you have a much bigger population, and you could do that with stars going behind. This isn't behind by a lot, because in fact the population that's probably going to dominate you is the population that's very close, which means the time scale is going to be pretty short. It's going to be on order of months, which actually makes for a nice experiment.
So I just had a question about the infrared flares.
Yeah.
What can you tell us about, what's the emission mechanism?
Yeah, this is what's the emission mechanism, how you're putting all these, the flux together. So the stuff that I trust the most right now is you can look at the colors in the infrared, because presumably the emission that's giving rise to the infrared from 1 to 5 microns is the same, and you can test that over short time scales. And what you see there is that no matter how bright it is, it's always the same slope. Okay, and the slope is pretty close to 0 in FNU space. So that's presumably synchrotron emission is what is giving rise to the infrared. That's also, and it's assumed that it's inverse Compton emission in the X-ray. And I'd say that's about all we're probably sure of. It's.
Okay, so any other questions? Otherwise, thanks, Andrea, and we'll see you here.